All right, let's continue with Chapter 4, the Bernoulli equation and pressure variation. In this chapter, or this section, we're going to apply Euler's equation to describe pressure variations in a fluid. So let's skip ahead to section 4.5, and we'll be right here. And the section is applying Euler's equation to understand pressure variation. And so this derivation is quite similar to that, to what we used looking at hydrostatics, except at this point we're not going to we're going to allow the fluid to flow, and we won't. Therefore the sum of the forces is going to have to equal the mass times acceleration instead of it being zero. So if you look back in the previous chapter when we derived the hydrostatic equation, we set the forces all equal to zero because the fluid was static. But in this case, we're allowing it to move. So this is a similar type of situation to what we did before. It uses kind of the similar nomenclature and so forth. The one thing that I want to remind you of and draw your attention to is that the pressure on any surface in a fluid is normal to the surface, since pressure is compressive. So we note here that on both ends of this fluid parcel, the pressure is inward into the volume. And so these two pressures are actually in opposite directions. That's going to be important. We'll see in a minute. And also remind yourself here of the geometry of these, basically how the distances in both z and along the parcel L, along the axis of the parcel, depend on alpha, because that is used in the derivation. So I'm not going to go through this in too much detail because we did this in hydrostatics. The only difference here is that we now, instead of setting the sum of the forces equal to zero, we set them equal to mass times acceleration. And this acceleration now is the acceleration along that L axis, along the axis of the fluid parcel. So basically, we're going to have a pressure force, like we've dealt with before, and a gravity force. And the combination of these two is just going to give us the piezometric pressure, basically, or piezometric force due to the pressure. And then we'll set it equal to ma. So it's basically the same exact derivation for hydrostatics, except on the right-hand side we have m times a, mass times acceleration. So as before, the pressure force turns out to be this. Note that, again, since these two pressure forces on either end of that fluid parcel are in different directions, we have a minus sign here. And because the way the definitions are, this becomes a negative quantity, negative delta P times area, where area is the area at the end of this fluid parcel. This is the area. So, so the way this is defined is that this is a larger pressure than that, even though it isn't. That's because that's where the negative sign comes from. So the negative is here. And then also the gravity term is also negative because y is defined to be upward, vertical, and the gravity is downward. So when we combine these two equations here, we see that we've got this pressure force, the delta P times delta A, minus the weight of the fluid. And again, we've substituted delta Z, delta L for the sine alpha here, as we could see that from the triangle that I showed you before. And then on the other side, we've got basically mass times acceleration, where the if I just write this out, the mass equals the density times the volume. So and in this case, the volume is delta L along the the fluid parcel, and we have delta A being the area of the cross-sectional end of it. So this is just MA. And what that results in is something that looks very similar to the piezometric equation that we had before, but this term now on the right-hand side is not zero. Remember, when we had zero here, this led us to the fact that piezometric pressure in a given fluid of a given gamma was conserved. So anywhere within that fluid parcel, this quantity, P plus gamma Z, this was conserved. But now that's not the case, because we have, if the fluid is moving, we have a resulting acceleration. So in vector form, this del uh, over del L becomes a delta, or a gradient. Basically, this is a gradient symbol, and this is basically the variation, the spatial variation of the pressure in the fluid. Note that because of the minus signs in both the pressure force and the weight of the parcel, this is in the opposite direction of the acceleration. So let's take a look at some cases. Let's look at the physical interpretation. So what we have here is minus the gradient of the piezometric pressure field, where piezometric pressure again is the pressure plus the gamma Z, the density times the acceleration of the particle. That's going to be our force balance, basically. And we can see that the acceleration acts in the opposite direction of the pressure gradient. So if the acceleration is in a positive direction, the pressure gradient is in, or the change in pressure with space, the pressure gradient is in the opposite direction. So let's look at a couple of cases. The first case we return to is looking at our sphere again, where we have this uniform flow field, uniform and steady flow field, and it's coming up and going around this sphere. And we already talked about in the previous video about how this is a stagnation line. So this fluid is actually decelerating. And what we have here is that, in fact, since we know the acceleration is to the left, we have to have the pressure gradient being to the right. And so if we look here, because this particle is slowing down, the acceleration vector must be tangent to the path and acting to the left, just like we saw before. And because of that, through Euler's equation, the pressure must actually be increasing in this direction to basically balance that. Now, these vectors aren't given the same magnitude because, in fact, the A is the acceleration, not the density times the acceleration. And this is the pressure gradient. So in case 2 here, we're looking at pressure variation normal to rectilinear streamlines. And so we're looking at a situation here where we have a uniform flow with depth here. We have streamlines being all very uniform in this fluid here, with actually no viscous effects at the boundary. So this is what we would call an inviscid flow. So let's go through the steps here. So we've drawn, we know we have the streamlines here. This is indicating constant flow. We're drawing a line that's normal to the streamlines here. We're recognizing that the normal component of the acceleration for this particle must be zero, because there's no curvature to any of these streamlines. Therefore, there's no normal component. So the only acceleration that we can have in this fluid is going to be tangential. Because that normal acceleration is zero, the pressure gradient along this line must also be zero. So there's no pressure gradient along the line. At a given depth, basically the piezometric pressure is constant and it's not changing. There's no spatial variation to the piezometric pressure. And we can conclude then that the piezometric pressure must be constant along this line, and therefore the pressure variation normal to the rectilinear streamlines is hydrostatic. So that's another case that we can derive from Euler's equation. Now finally, we might have a case where we have curved streamlines. And here, in this case, we can see we have flow that's curving around something. We actually might have a sphere or a cylinder down here, just with the flow coming in here and going around this object. So in this case, we know we have, even if the speed does not change along these, although it probably is, but if the speed isn't changing, because we have a curved streamline, we know we're going to have acceleration inward towards the radius of curvature of these streamlines. So we have to have an acceleration. And this rho A force here must be balanced by the pressure gradient. So whenever we have a curve like this, we must have an increasing pressure outward away from the center of curvature. So with the rho A, or the acceleration normal to the curved lines, we have to have this pressure gradient developing in the opposite direction due to Euler's equation. So that's it for section 4.5. There's a couple of interesting examples that I'll do in separate videos. This is very important. Euler's equation is used when we start to talk about Bernoulli's equation. So you can see we're going to develop Bernoulli's equation next time, starting from Euler's equation. Very important stuff.